The next trend that we're going to look at is ion sizes. So some compounds are composed of particles called ions. An ion is an atom or a group of atoms that has a positive or negative charge. Atoms are neutral because the number of protons equal the number of electrons. So positive and negative ions are formed when electrons are transferred, either lost or gained between the atoms. So let's talk about how an ion is made. Let's take a sodium atom. Sodium is atomic number 11, so it means it has 11 protons. Remember, the atomic number also equals the number of electrons, so it has 11 electrons. Protons have a positive charge and electrons have a negative charge. So if I have 11 positives and 11 negatives, that's an overall charge of 0 or neutral. Sodium atoms are neutral. But metals tend to lose electrons from their outer energy level. We'll talk about why in a minute here, but all metals lose electrons from their valence shell. So sodium has 1 electron in its valence shell and it's going to lose it. So now it's going to have 11 protons but only 10 electrons. So it's going to become a positively charged particle, which we also call a cation. So here's the math. We still have 11 protons, but now we only have 10 electrons for a net charge of +1. So I can't just write Na because that means sodium. I have to write Na and then give it a charge, that +1 written above it, superscript. That would tell the reader that is a sodium ion and not a sodium atom. So let's talk about nonmetals. So let's take chlorine. Chlorine is atomic number 17, so it has 17 protons and 17 electrons. So 17 positive charges is balanced out by 17 negative charges to be a neutral chlorine atom. So nonmetals like chlorine tend to gain 1 or more electrons, and chlorine is going to gain 1. So now I still have my 17 protons, or else it's not chlorine, and I now have 18 electrons. So I have 1 more negative charge than I do positive charge. So the net charge here is -1 or 1 minus. So you would write chlorine with a little 1 minus or just minus to write a chloride ion. So why do ions gain or lose electrons? Well, we talked about how electrons or atoms like to be stable, and full energy levels require lots of energy to remove their electrons. So these are the noble gases. They all have full orbitals, so they're the most stable elements on the table, which is why they rarely take part in any chemical reactions. So atoms behave in ways to try to achieve a noble gas configuration. They're either going to gain electrons to become like a noble gas or lose electrons to have an electron configuration like a noble gas. So ions always have a noble gas configuration, so a full outer level. So let's take sodium for example. Sodium's configuration is 2-8-1. It is a metal, so it's going to lose electrons. It is going to lose that 1 valence electron it has to become a +1 sodium ion, and its configuration is now 2-8, just like neon, a noble gas, a stable noble gas. Metals always form ions with the noble gas configuration that came before them because they do this by losing electrons. Here's sodium, and it is turning into the same configuration as neon, which came before sodium. If this question was about potassium, it would turn into the same configuration as argon. So all ions always have a noble gas configuration. So if I have a nonmetal like oxygen here, its configuration is 2-6, not quite a noble gas configuration. So nonmetals like oxygen tend to gain electrons. Oxygen is going to form a 2- oxide ion by gaining 2 electrons. And it's going to move over to be just like neon. So instead of 2-8, the configuration for oxygen, it's going to be instead of 2-6, it's going to turn into 2-8, just like neon again. Nonmetals are always going to form ions with the noble gas configuration that comes after them. So just like oxygen became neon, it gained 2 to become like neon. Fluorine would have only gained 1 to become like neon. Chlorine would gain 1 to become like argon. Phosphorus would gain 1, 2, 3 to become like argon, the noble gas that comes after it. So when we're talking about the trends in ionic size, so now that we know about ions, we need to talk about the trends in ionic size. It's really the same as the atomic size trends. It's just that your explanation for these types of questions might be a little bit different. So first let's talk about cation trends. Remember, cations are another name for a metal ion. When a metal loses electrons, it becomes a cation. So here's a question. Compare the size of a lithium ion to a sodium ion. So let's first look at it as a lithium atom. So lithium has a nucleus in the middle. It has 3 protons, and it has one shell that has 2 electrons in it, and then it has a second shell which has 1 electron in it. Let's look at sodium, the element underneath it. It has a nucleus with protons in it as well, and it has one shell that has 2 electrons in it, and a second shell that has 8 electrons in it, and it has a third shell, because it's in period 3 here, that has 1 electron in it. So it has 3 shells. So if I asked you to compare a sodium atom to a lithium atom, you'd say sodium is bigger. It has 1 more shell than lithium. But I'm not asking about atoms, I'm asking about ions. Now these are metals. So remember, metals lose electrons to become cations. So lithium is going to lose that electron, sodium is going to lose that electron. But if you lose an electron out of your valence shell, there's no reason to have a valence shell. That shell goes away. So would sodiums. They would both become ions with a +1 charge, but instead of lithium being 2 shells big, now it's only 1 shell big. And instead of sodium being 3 shells big, it is now 2 shells big. So sodium is still bigger because it has more shells, but it has 2 shells instead of 3. It's the only difference in this type of question here. Now, besides the shell number decrease, which is making the ions smaller, the protons in the nucleus have less electrons to pull in. The pulling power didn't change. We didn't lose protons, but we lost electrons. So now the protons in the middle can pull those outer electrons in closer. So they get smaller when they become cations as well. So let's look at another type of question here. So rather than comparing 2 atoms, which is kind of an easy question, this is a very typical question. It says compare the size of a sodium ion to the size of a sodium atom. Let's draw them out here. So sodium's configuration is 2-8-1. So we have our nucleus, we have our first shell with 2 electrons, our second shell with 8 electrons, and our third shell with 1 electron. Now a sodium ion is the same configuration, but to become that ion, it's lost that valence electron out of the third shell. It's only 2 shells big. So the answer is, of course, a sodium ion is smaller than a sodium atom because it has less shells. Now, you could probably get the answer right if you said it has less electrons, but less shells is a better answer. The fact that it has less shells is what's making it drastically smaller than a sodium atom. So cations are always smaller than the atoms from which they come from, because not only do they lose electrons to become smaller, they lose a valence electron shell. All right, next let's look at anion trends. So remember, an anion is an atom that has gained electrons to become an ion. So we're talking about nonmetals. So compare the ionic size of a nitride ion and a fluoride ion. So nitrogen has 7 protons and 7 electrons. It's going to gain electrons to become an ion, but it still has a pulling power of 7. Fluorine has 9 protons and 9 electrons. It's going to gain 1 electron, but it still has a pulling power of 9. Pulling power of 9 is going to beat a pulling power of 7, no matter how many electrons they gain. So fluorine is going, or a fluoride, I should say, a fluoride ion is always going to be smaller because it has more protons to pull the electrons in closer. So the period trends stay the same. As you go to the right, you get more protons, you pull those electrons in closer, and you become a smaller ion. Okay, next let's look at a question like this. It says compare the ionic size of a fluorine atom and a fluoride ion. So fluoride is bigger because it has one more electron. So they still both have two shells, but the pulling power in the middle has stayed the same. If you are a atom with a pulling power of 9 and you're pulling in 9 electrons, you can pull them in a certain width, a certain distance. You'll have a specific radius. Now a fluoride ion gained that 1 electron to fill its outer shell, but its pulling power is not any stronger. So those electrons are going to be allowed to migrate a little bit further away because the protons in the middle can't influence them as strong as they did when there was only 9 of them. So anions are always larger than the atoms that they were because the pulling power of the nucleus doesn't change, but the amount of electrons that you're pulling in gets bigger, so the electrons are allowed to move a little further away. So in summary here, an ion is an atom or a group of atoms that have a charge. Metals lose electrons and become smaller positively charged particles, which we call cations. Not only do they lose electrons, but they lose an entire energy level, so they get smaller. Cations, when they lose electrons, they always achieve a noble gas configuration that comes before them on the table. Nonmetals gain electrons and become larger negatively charged particles called anions. They become larger because their nucleus has a greater area to cover and those electrons migrate a little bit further away from the nucleus. Remember, anions, when they gain electrons, they're going to gain as many as they need to achieve the noble gas configuration that comes after them. In this chart here, you can copy this down in your notes. You can make a sketch of this. This just summarizes the atomic size and ionic size. They increase in the directions of the arrow. So as we go down, atomic size gets bigger because we get more shells. Ionic size also gets bigger because there's more shells. Even though they're losing shells, as you go down, there's more shells on the bottom than there are on the top. And this size increases also going to the left. As we move to the left over across the periodic table, you have less protons, and less protons means less pulling power, and those outer electrons can migrate further and further away from the nucleus. So that's ion trends. Next we'll be talking about electronegativity and first ionization energy.